Good evening. 82 years ago, American astronomer Karl Jansky constructed the world's first radio telescope and discovered radio waves coming from the Milky Way, which paves the way for a new branch of astronomical research. Last month, the final antennae for the large millimeter, submillimeter array ALMA project was handed over to the observatory by the European AEM Consortium to complete the world's largest radio telescope complex in Chile. Therefore, in this month's programme, our main theme is radio astronomy. But first, the BBC TV programme, The Sky at Night, is under threat of being axed after 56 years. The programme was hosted by TV astronomer Sir Patrick Moore most of that time. It is a special education programme which has encouraged a generation of people to take up astronomy as a hobby and begin science subjects at colleges and university. Please help save this magnificent astronomy programme by signing Karen Barker's online petition at change.com. So far, Karen has over 45,000 signatures and more are urgently needed, so please spare a moment to pay a visit and add your signature to help save this great British institution. Also visit our own website at Astronomy TV Programme at blogspot.co.uk. Now let's take a look at the highlights for November, and we begin with the total eclipse of the Sun on November the 3rd. Totality will be visible from the northern Atlantic Ocean, east of Florida, to Africa, Gabon, with a maximum duration of 1 minute and 39 seconds, visible from the Atlantic Ocean, south of Ivory Coast and Ghana. Sadly, the eclipse is not visible from the UK or the North Americas. Our Earth is the third planet out from the Sun, lying at a mean distance of 93 million miles, and the Moon is our own natural satellite, orbiting around our planet at a mean distance of 238,000 miles, and it takes just over 27 days to do so. The diameter of the Moon is 2,159 miles. An eclipse of the Sun occurs because by sheer chance the angular size of the Moon, which is about 32 arc seconds, is identical to that of the Sun, which is 400 times further away from us. On rare occasions, the Earth, Moon and Sun line up, and that's when the Moon passes across the face of the Sun. A total eclipse of the Sun is the only time when the Sun's white atmosphere, known as the corona, can be seen by local people. The distance between the Moon and the Earth varies from around 221,500 miles to 252,700 miles, and the extreme perigees, closest to the Earth, and apogees, furthest from the Earth. Therefore, if an eclipse takes place when our Moon is close to its apogee, its angular size is not great enough to cover the Sun, and we therefore have an annular solar eclipse. Eclipses don't happen every month because the Moon's orbit is inclined by a little over 5 degrees relative to the Earth's, so that at most new moons it is either above or just below the Sun in the daylight sky. During a solar eclipse, the Moon's inner shadow, we call the umbra, moves rapidly from west to east across the Earth. The width of the track of a central eclipse varies according to the relative apparent diameters of the Sun and Moon. In the most favourable circumstances, when a total eclipse occurs very close to perigee, the track can be over 156 miles wide, and the duration of totality may be over 7 minutes. Outside of the central track, a partial solar eclipse is seen over a much larger area of the Earth. Typically, the umbra is 62 to 100 miles wide. There is increased activity in the number of solar flares around the Sun's disk at the moment, so we can expect this month's solar eclipse to be of great interest to astronomers. Whatever comes into view, photographs of the event will be as magnificent as ever. The planet Mercury is at inferior conjunction on the 1st of November. Its phase is new and will not be visible. The planet then starts to move around and away from the Sun and will become visible in the southeastern sky before dawn, shining at magnitude -0.3, Mercury reaches greatest eastern elongation on November the 18th at 19.5 degrees from the Sun. The planet then rises 3 hours before sunrise in the constellation of Virgo. On the morning of November the 26th, the planet Saturn will be less than half a degree north of Mercury in the dawn sky. The planet Venus is at greatest western elongation of 47 degrees from the Sun on November the 1st, when it can be seen as a brilliant star-like object in the southwestern sky after sunset, shining at magnitude -4. The planet's disk is then 49% illuminated, which is known as dichotomy, and is visible in binoculars. At the end of the month, Venus sets 2 hours 40 minutes after the Sun, shining at magnitude -4.3, when the planet's disk will be 31% illuminated. It will then look like a large crescent. This is an ideal time for amateur astronomers to look for the subtle glow of the night side of Venus, known as the Ashen light. To stand a good chance of seeing the phenomenon, use the slow motions on your telescope to position the brilliant portion of Venus's disk just outside of the field of view, and then look carefully at the dark side of the planet. Another method is to use an occulting bar, an opaque mask for one's eyes. This lens blocks the sunlit portion of Venus, which greatly cuts down the extraneous light that is scattered into the eye, improving the chances of witnessing the faint ashen glow. The ashen light was first sighted by astronomer Giovanni Riccoli on January the 9th, 1643, and has been frequently sighted by various amateur astronomers since then. The cause of this subtle glow remains a mystery. Some astronomers suggest that it may be caused by aurora activity in Venus's upper atmosphere. Here on Earth, we call these the northern lights. Now what about the Moon? New Moon is on November the 3rd. First quarter will be on November the 10th, when it will be in the constellation of Capricorn. Full Moon will occur on November the 17th in Taurus, the Bull, and last quarter is on November the 25th, when it will be in the constellation of Sextans. The best photo opportunity this month will be on November the 18th, when the Moon will be seen in the Hyades, the distinctive open cluster marking the head of Taurus the Bull. Soon after sunset, look into the western sky and you will see the bright orange star Aldebaran 2 degrees to the west of the Moon. The planet Mars is visible in the eastern sky before dawn, rising 2 hours before the Sun on the 1st of November. The planet can then be seen below the main body of Leo the Lion, shining at magnitude +1.6. Mars continues to move along its celestial path during the month into the nearby constellation of Virgo, when its magnitude fades a little to +1.4. The planet will then rise 4.5 hours before the Sun at the end of November. Sadly, Mars has a small angular diameter at the moment, so that a large telescope of at least 8 inches, that's 20 centimetres, is needed to show any detail on the planet. The giant planet Jupiter is now a brilliant evening star in the eastern sky after sunset, shining at magnitude -2.2 in the constellation of Gemini, the Twins. The planet lies to the lower left of the star Delta Gemini, named Wasat. Jupiter is visible throughout November in a dark sky and will reach opposition on December the 3rd. Jupiter is a lovely sight in small telescopes, and even a pair of binoculars will easily show the planet's 4 Galilean moons, Io, Europa, Ganymede and Callisto, as they slowly drift around the planet. The Leonid meteor shower runs annually from November the 6th to the 30th, producing an average of up to 100 meteors per hour at its peak. This shower is unique in that it has a cyclonic peak about every 33 years, where hundreds of meteors per hour can be seen. The last of these occurred in 2001. The Leonid is produced by dust grains left behind by comet Tempel-Tuttle, which was discovered in 1865. This year, the Leonid's peak on the night of the 16th and the morning of the 17th. Unfortunately, the glare from the full moon will block many of the meteors this year, but if you are patient, you should still be able to catch quite a few. Now for an update on comet ISON. The comet will cross the Earth's orbital path on October the 31st and will then be speeding towards the Sun at 26 miles a second. Observations and images taken by members of the comet section of the German Astronomy Club over the last month indicate that the magnitude of the comet ISON is on average 1.5 magnitudes fainter than predicted, indicating that it is not brightening en route towards the Sun. The comet's nucleus, estimated to be 2 miles in diameter, is tiny. However, careful study of the latest images suggests the nucleus is still intact. The coma spreads out evenly from a single point, which we wouldn't see if ISON were falling to pieces. In fact, the symmetry of ISON's coma suggests that the comet's entire sun-facing surface is feeding the coma. No jets of gas have been spotted. Without a jet to spin it around, ISON isn't rotating very much. This means that the comet's ephemeris is had to be recalculated, and this last occurred on October the 16th by the Faculty of Exact and Natural Sciences, Institute of Physics, Medellin, Colombia. The new predictions show that comet ISON will be at magnitude plus 8.9 on October the 30th, plus 8.2 on November the 15th, and plus 6.6 on November the 28th, which is also the date of the perihelion when comet ISON skims 724,000 miles above the surface of the Sun before beginning its outward journey. Comet ISON will then be travelling at 146 miles a second. As a useful guide, the naked eye can just about see stars of magnitude plus 6 in a clear dark sky, where binoculars will easily show comet ISON up until the end of the month. On October the 14th, amateur astronomer Christine Bull became the first amateur astronomer to obtain comet ISON spectra using an LP600 spectrograph on an 8-inch telescope at the Castanet-Toulson Observatory near Toulouse in the south of France. His data shows two C2 diatomic carbon emission lines and a probable faint signature of CN, cyanide radical. Both of these are common in comets. The former is likely to be responsible for the green glow that some images of ISON are now showing. Now let's move on to our main theme. The story of radio astronomy goes back over 190 years, when the first experimental work on the connection between electricity and magnetism began around 1820 with the work of Hans Christian Ørsted and continued with the work of others, including André Marie Ampère and Michael Faraday. These investigations culminated in the complete theory of electromagnetism, developed by James Clerk Maxwell. This theory describes the theoretical basis of the transmission of electromagnetic waves. Light is an electromagnetic radiation that moves in waves. In physics, the wavelength of a wave is the spatial period of the wave, the distance over which the wave's shape repeats, which is known as a wavelength and is measured in Armstrong units. The frequency is the number of occurrences of a repeating event per unit of time, which is measured in megacycles per second. The naked eye is sensitive to the visible spectrum that lies between 400 and 700 Armstrong units. As the wavelength increases, we encounter the infrared, microwaves, and then the FM, AM, and long-range radio waves. At the other end of the scale, as the wavelength decreases in size, we come across ultraviolet rays, X-rays, and gamma rays. The eye is only sensitive to the wavelengths of the visible spectra. Therefore, as an amateur astronomer, every time you study a planet or deep sky object by looking through a pair of binoculars or a telescope, you are carrying out optical astronomy. However, the eye is much less sensitive to colours than CCD devices or digital cameras, so we don't see the same distinct colours we find in the magnificent coloured photographs in books and magazines. Radio telescopes are different to optical telescopes in that they consist of a large parabolic dish for collecting radio waves from space. You don't look through a radio telescope, the radio waves are collected and processed by a receiver. Only then can the observer listen to the radio signal from the object under observation, or it is printed out. Today these signals are processed by powerful computers into coloured depictions of the object and its surroundings. Radio astronomy dates from the early 1930s, when Karl Jansky in America was investigating the problems of static. During the course of his experiments, he discovered that radio emissions was coming from the sky, and he tracked it down to certain regions of the Milky Way. This research was fundamentally important, but curiously enough, Jansky never followed it up, and his work attracted little attention at the time. Shortly before the outbreak of war, another American amateur named Grote Reber began experimenting on his own account, and he built a 30-foot parabolic dish, and working on frequencies in the region of 150 to 160 megacycles per second, not only confirmed Jansky's results, but actually produced a chart of the radio sky. It may justly be said that Reber's paraboloid was the first radio telescope deliberately built for such a purpose. It must be remembered that Jansky's original detection of radio waves from the Milky Way was not the result of a deliberate search. I must add that not all radio telescopes are paraboloids, or the type used by Reber, and are now well famous owing to the 250-foot dish at Jodrell Bank. Sometimes a fixed array of aerials will suffice for an investigation. In this case, the telescope will be steered by the rotation of the Earth on its axis. Alternatively, a large number of small systems may be grouped together. In other cases, a large aerial may be used in a fixed position, together with a small movable aerial. There are in fact many different patterns, each with its own advantages and drawbacks. The Jodrell Bank Observatory was established in 1945 by Sir Bernard Lovell, a radio astronomer at the University of Manchester, who wanted to investigate cosmic rays after his work on radar during the Second World War. It has since played an important role in the research of meteors, quasars, black holes, pulsars, and was heavily involved with the tracking of space probes at the start of the space age. The site of the observatory, which includes the Jodrell Bank Visitor Centre and an arboretum, is located in Cheshire in northwest England. The main telescope at the observatory is the Lovell Telescope, which is the third largest steerable radio telescope in the world. There are three other active telescopes located at the observatory. Jodrell Bank Observatory is also the base of the multi-element fibre optic link interferometer network, Merlin, a national facility run by the University of Manchester on behalf of the Science and Technology Facilities Council. Interferometry is a family of techniques in which waves, usually electromagnetic, are superimposed in order to extract information about the waves. Interferometry is an important investigative technique in the field of astronomy. Astronomers using different radio telescopes around the planet to observe a single object in the universe record their observations using a very precise atomic clock for reference. The individual observations are then combined in a powerful computer to produce a single radio image. An astronomical interferometer achieves high-resolution observations using the technique of aperture synthesis, mixing signals from a cluster of comparatively small telescopes rather than a single very expensive telescope. Early radio telescope interferometers used a single baseline for measurement. Later astronomical interferometers, such as the Very Large Array, use arrays of telescopes arranged in a pattern on the ground. A limited number of baselines will result in insufficient coverage. This was alleviated by using the rotation of the Earth to rotate the array relative to the sky. Thus a single baseline could measure information in multiple orientations by taking repeated measurements, a technique called Earth rotation synthesis. Baselines, thousands of miles long, were achieved using this long baseline interferometry. The final antenna for the Atacama Large Millimeter Submillimeter Array ALMA project has just been handed over to the ALMA Observatory. The 36-foot, 12-meter diameter dish was manufactured by the European AEM Consortium and also marks the successful delivery of a total of 25 European antennas, the largest European sub-observatory contract so far. The radio telescope is the 6-6 and final antenna to be delivered to the observatory. North America has provided 25 12-meter dishes, while East Asia has delivered 16, 4 12-meter and 12 7-meter. This delivery of the last antenna a month ago completes the ALMA construction phase and provides all 66 dishes for science use, marking the beginning of a new era of discoveries in radio astronomy. ALMA will help astronomers answer important questions about the origin of the universe. The telescope observes the universe using light with millimeter and submillimeter wavelengths between infrared light and radio waves in the electromagnetic spectrum. Light at these wavelengths comes from some of the coldest but also from some of the most distant objects in the cosmos. These include cold clouds of gas and dust where new stars are being born, and remote galaxies towards the edge of the universe are observable. There are a host of exotic objects in the universe that astronomers would like to study in more detail, including the class of stars known as pulsars, which were first detected on November 28, 1967 by Jacqueline Bell Burnell and Anthony Hewish using the 250-foot dish at Jodrell Bank. When a massive star comes to the end of its life, it can implode in a massive supernova explosion, crushing the star material into what we call a neutron star or pulsar. The star is so compact that just a teaspoon of its material can weigh many tons. Today pulsars rotate extremely rapidly after their creation due to the conservation of angular momentum. Like a spinning ice skater pulling in their arms, the slow rotation of the original star's core speeds up as it shrinks. A newborn pulsar can rotate several times a second. Sometimes the pulsar absorbs orbiting matter from a companion star, increasing the rotation to several hundred times per second, reshaping the star into a flattened spheroid. Over time, pulsars slow down because their rotating magnetic fields radiate energy. A magnetostar is a type of pulsar with an extremely powerful magnetic field, the decay of which powers the emission of high-energy electromagnetic radiation, particularly X-rays and gamma rays. The theory regarding these objects was proposed by Robert Duncan and Christopher Thompson in 1992. SGR 1806-20 is a magnetostar, a particular type of pulsar. It was discovered in 1979 and has been identified as a soft gamma ray repeater. SGR 1806-20 is located about 50,000 light-years from the Earth on the far side of the Milky Way in the constellation of Sagittarius. It has a diameter of no more than 12 miles and rotates on its axis every 7.5 seconds. On December 27, 2004, the radiation from an explosion on the surface of SGR 1806-20 reached the Earth. The gamma rays it produced struck the ionosphere and created more ionization, which briefly expanded the ionosphere. The magnetostar released more energy in 1/10 of a second than our Sun has ever released in 100,000 years. Such a burst is thought to be the largest explosion observed by humans in our galaxy since the supernova observed by John Kepler in 1604. Black holes are mainly found in the centre of galaxies in the universe, including our own. A black hole forms when a massive star destroys itself in a supernova explosion, leaving behind a supermassive singularity. Its gravity is so powerful that not even light can escape its attraction. Active galaxies fueled by black holes inside them are called quasars. A quasar-stellar radio source is a very energetic and distant active galactic nucleus. Quasars are extremely luminous and were first identified as being high redshift sources of electromagnetic energy, including radio waves and visible light, that were pinpoint-like, similar to stars, rather than extended sources similar to galaxies. A blazar is a very compact quasar associated with a presumed supermassive black hole at the centre of an active giant elliptical galaxy. Blazars are among the most energetic phenomena in the universe and are an important topic in extragalactic astronomy. Blazars are members of a larger group of active galaxies that host active galactic nuclei. The name blazar was originally coined in 1978 by astronomer Edward Spiegel to denote the combination of these two classes of quasars. In April 2013, the night sky was flooded with the brightest display of gamma rays, the universe's highest energy light ever seen by astronomers. The culprit was a staggering flare-up of Markram 421 that was already in the known catalogue of blazars, having had something of a flare in 1996. Normally this active galaxy has a visual magnitude of plus 13.3, and it lies in the constellation of Ursa Major. In October, it was announced that two international teams of astronomers have used the power of ALMA to focus on jets from the huge black holes at the centre of galaxies and observe how they affect their surroundings. They have obtained the best views yet of the molecular cloud around a nearby quiet black hole and caught an unexpected glimpse of the base of a powerful jet close to a distant black hole. Two new studies, both published in the journal Astronomy and Astrophysics, use ALMA to probe black hole jets at very different scales. A nearby and relatively quiet black hole in the magnitude 10 galaxy NGC 1433 in the southern constellation of Herorium, and a very distant and active quasar called PKS 1830-211. ALMA revealed a surprising spiral structure in the molecular gas close to the centre of NG3 1433. This explains how the material is flowing into fuel the black hole. With a sharp new observation from ALMA, astronomers have discovered a jet of material flowing away from the black hole, extending for only 150 light years. This is the smallest such molecular outflow ever observed in an external galaxy. The discovery of this outflow, which is being dragged along by the jet from the central black hole, shows how such jets can stop star formation and regulate the growth of the central bulges of distant galaxies. It's fascinating to think that none of these exotic objects were known 82 years ago, so I wonder what new discoveries are awaiting us now that ALMA is fully operational. That's all we have time for this month. Thank you for watching. Please visit our website at Astronomy TV program at blogspot.co.uk. Until December, goodbye for now.